There we go. Okay, so let's get started. This is going to be the session on quantum physics. As usual, I have the introductory slides, which probably are relevant for quantum and actually for the philosophy later. So again, to remind ourselves, the goal of the project is to identify a handful of physical starting points from which we can derive the basic laws. And so the idea is to be able to say something like infinitesimal reducibility gives us classical states and irreducibility gives us quantum states. And the idea is that if we want really to do this in a precise way, this also means we're deriving the mathematical structure themselves from physical requirements. So, for example, rederiving the structure of topology sigma algebra from the logic of experimental verifiability. And again, one of the underlying perspective that we have is that we can have this hierarchy of things. There are things that exist, things that are experimentally accessible, and things that can actually be studied experimentally, that are repeatable, and we can make experiments. And the point is that physical theory, and for us, quantum mechanics for this session, is about things that are here. And we're going to see this more in detail. And then the physical theory themselves are typically idealized account of the empirical reality. So they are a model of this with some idealizations, and therefore the point for us is really to understand what are the requirements to be able to actually have something repeatable that can be studied experimentally, and what are the abstraction and realization that go into creating the physical theory. If this is our perspective, if physics is about creating models of empirical reality, then of course the foundation of physics should be a theory of models of empirical reality, something that tells us what models of empirical reality can and cannot do, in the same way that the foundations of mathematics tells us what a proof is and what can and cannot be proven, and the foundation of computer science tells us what a computation is and what are the limits on the space of computation. It means that we have a sort of a different approach to the foundations of physics. We're not really interested in constructing interpretation that add things that try to increase what's inside in the theory. Especially this is going to be true for today in quantum mechanics. We're not really trying to find a theory of everything from which everything, all the theories can be derived. But really, we're trying to create a theory about physical models, trying to understand what are the general principles and requirements in constructing a physical theory, what are the things that we have to describe to be able to describe experiments, and from that derive a general mathematical framework, and then have specific assumptions that derive the different theories, right? So this is sort of right now, physics is sort of a patchwork of different models and theories that you use because the problem looks like another problem that you read in a textbook. And so the idea is to sort of have some more clarity in why exactly we use this model for that particular system. And to do this, we have two approaches. One is reverse physics that start with the physical theory and reconstruct a small set of assumptions from which the theory can be reconstructed. And then we have an approach that is called physical mathematically, that is bottom up. You start from scratch, you start from the physical requirement, and you layer each axiom and definition with a physical justification to reconstruct the mathematical structure and the theory in more detail. This session is about reverse physics. Similar to the session of thermodynamics, we have a lot of ideas and pieces that we're putting together. It's not put together yet, so there is ample space to sort of better understand and contribute here. So the first thing to me, before starting talking about quantum mechanics itself, one of the things that I care is understanding why classical mechanics fails, because to really understand what quantum mechanics is and what is the realm of applicability, we also have to know why classical mechanics does not work in that realm of applicability. Essentially, what is quantum mechanics fixing that quantum mechanics, the classical mechanics doesn't have. And the typical scenario here, you basically just say, oh, classical mechanics does not agree with reality. We could have had the classical mechanics, but the reality is different. And that's a very unsatisfied answer because it doesn't really tell you what's going on. So there has to be something in classical mechanics that is broken and doesn't fit reality. And we need to understand what it is. So I have two ways of looking at this, two arguments. One is about essentially definition of the system. The idea is that to define a system, we have to have a boundary because we need to tell what is inside the system and what is outside. And typically measurements are, the measurement device is outside of the system because it has to be independent. You have to discover what the system is. And the interaction at the boundary the idea is that determines how the system can be defined. So for example, if you want to study the motion of a cannonball and you have a boundary, and so you have air that is scattering off its surface, that effect is going to be negligible. And so the state of the cannonball can be taken to be a precise value of positional momentum, because you can pretend that the system is completely isolated. Now, if you're instead studying the motion of a speck of dust, where the air scatters the speck of dust is not going to be negligible. You're going to have some kind of Brownian motion given by that. And so the state of that is not going to be a precise positional momentum. It will be a probability distribution because of the interaction of the environment, because of the type of boundary that you have. And now you could have something more catastrophic. You could say, I want to study the motion of a cannonball on the surface of the sun, and then there's going to be plasma that's scattered off the surface. The effect is catastrophic. The cannonball ceases to exist in any shape or form, and therefore you can't really talk about a cannonball on the surface of the sun. We can talk about cannonballs here and not there. And so the point, the interaction of the boundary is important for the very definition of the system. The boundary has to be such that at least the system remains itself. It's not destroyed. And it seems kind of trivial, but it's there. And this issue is that in classical mechanics, you pretend that it's not there. Classical mechanics assume that objects can be adequately isolated, that basically nothing happens on the boundary. The system, it is, and it is what it is. But it also assumes that we can study parts of the objects, and these parts can be as small as we want. And so now you have a kind of a problem here, because for a large system, you can indeed assume that the system is isolated, but at some point, if you take smaller and smaller parts, these small parts cannot be assumed to be isolated anymore. So you are going to arrive at a point in which this description does not work anymore. So this idea of infinitesimal reducibility, the idea that we can take a system and study the part that are smaller and smaller and smaller, this sort of it's a contradiction with the assumption of isolation, that the system can evolve by itself. So this is one argument that we have. That classical mechanics fails because we can never isolate the system, because on practical grounds, we simply cannot do it. We can have a system that are perfectly isolated. It's an idealization. On theoretical ground, we cannot shield the gravitational interaction. We cannot eliminate thermal radiation. So there is always something that is interacting with the system. And on logical ground, because complete isolation means that no possible interaction with the system can happen. So signals will pass through, there would be no possible measurement and no gravity. Basically, the system disappears from the universe. So because we can never completely isolate the system, because there is always some interaction, we can never think that the description that we have for a physical system that we're studying is completely accurate. And so we are going to have some statistical probabilistic nature. And again, notice that we're talking about making a model of the system, not some ontological property that the system has because it has the system. No, the system is defined by the boundary that I've put in. I'm talking about the cannonball because I'm here and I have a particular boundary. So it's all practical and operational. It's not something that exists independent of the reality that is around the system itself. So this is one set of argument. The other set of argument is simply by looking at the entropy. And of course, the entropy is there as a measure of the interaction between the system and the environment. So it's basically the same argument in another form. The first thing that you note is that if you take a microstate, the phase space volume of the microstate is 0, and therefore the entropy would be minus infinity. The same things if you calculate the entropy with the Gibbs-Shannon entropy, you would have a delta Dirac, and the delta Dirac has an entropy of minus infinity. So the point here is that the entropy of a pure microstate in classical mechanics is minus infinity. And this is somewhat of a problem, because if you remember the third law puts a lower bound of the entropy at 0. And in fact, if you look at the laws for an ideal gas in classical mechanics, as you decrease the temperature, the entropy goes to minus infinity. So of course, in this region, as we lower the temperature, the classical mechanics is just gonna say nonsense. And instead, quantum mechanics has the two different statistics, and both these statistics modify this distribution to go to 0 when we have entropy. So we have a fundamental problem that classical mechanics is inconsistent with the third law of thermodynamics. So that's not good. It can also be seen to be a contradiction with the second law of thermodynamics, because if we have a system with minus infinite entropy, it sort of provides a loophole, because minus infinite entropy plus a finite delta in entropy is still minus infinity. And so we can effectively dump all the entropy increase into it, and we can essentially create a system that does whatever it wants without increasing the entropy of the system, which of course would not make sense. And another more logical reason that we saw yesterday on the meaning of the zero entropy, we can understand the zero entropy that is the entropy of an empty system. If we have an empty system, then the empty system added to another system just give you the same system. And since the entropy must be additive, you must have the entropy of the system has to be 0. And from an informational perspective, you're basically saying that that's the best description that you can have, and you can't have something that is better prepared or better described than just saying that the system is not there. And so from an information theory perspective, from a thermodynamics perspective, no system can have an entropy lower than 0. It just doesn't make sense. So classical mechanics, you can say that fails because it allows for the possibility of statistical ensembles that can never exist. On practical grounds, it would allow us to bypass the second law, so that doesn't really make sense. On theoretical grounds, they fail to respect the third law. And then on logical grounds, they would provide more information about the system. The state of the system does not exist, which is already a complete description of the system, which doesn't make sense. And so the point is that quantum mechanics is there to address this, because all pure states have 0 entropy and mixed states have positive entropy, and therefore this loophole is essentially fixed. So the takeaway is that classical mechanics actually fails at conceptual level, and this we think so. It's not just a matter of, oh, it doesn't work experimentally. There's something conceptually wrong that doesn't fit as a model for reality. Because it doesn't take account the relationship between system and environment. It assumes a perfect isolation at all scales, which it doesn't hold, and it does not provide a lower bound on entropy. And again, these two things are actually the same things, they're related to each other, they're not independent. Okay, so if we agree with this perspective, now let's go and try to sort of deconstruct in the reverse physics way quantum mechanics to try to understand what these pieces of machinery are and how we can understand them better in a way that doesn't use any weird, hidden variables or parallel words, or things that are in the metaphysical reality that they're not in the empirical reality. So the idea is going to be essentially that quantum mechanics and states of quantum mechanics are equilibria in the same way that they are that you have equilibria in quantum mechanics, that projections are just changes from one type of equilibrium to the other. And the context of quantum mechanics, the things that things are not always well defined, basically maps to the fact that you're putting the system in different boundary conditions in the same way that you would do in thermodynamic and statistical mechanics. So that's the general idea. Let's go and see in the details how this works. So in quantum mechanics, you have an observable that it's a Hermitian operator, and then you have a set of eigenstates and eigenvalues. And the eigenstates and eigenvalues fully describe the Hermitian operator you're observing. For each observable, the idea that when you make a measurement, you make a projection, you have an incoming state, and you do your measurement, and then the output is one of the eigenstates with the probability given by the Born rule. And one of the key things is that if you were to repeat the measurement, that all these things, since they are eigenstate, they would be projected to itself, that they wouldn't change. And so the eigenstates are things that they are left untouched by the projection. And we already have something, a word for that. It's just an equilibrium. So if you think this is a process, the eigenstates are just equilibria of the process. And that's it. There is already we find this notion of equilibrium coming. Now, what one can say, not just that eigenstates are equilibrium of a process, we can also say that all quantum states are eigenstates of some observable. And the simplest observable that you can imagine is the projection, is the observable that gives you 1 for that state and 0 for all the other eigenstates. And you can always construct this mathematically, and physically it means you can recognize the state that you prepare. And if you can't recognize the state that you prepare, you would have a physical problem. So this is a physical thing that you must have. And so if all quantum states are eigenstates of an observable, then it means that all quantum states are equilibria of some measure. And we can also show that there are also equilibria of a unitary process, because every observable generates a unitary transformation. So if I have an observable, I can create, this shouldn't be a D here. This is something that we corrected and then it cropped up. It can be an exponential of O alpha over IH bar. And this operation is going to be a unitary operation exactly because this is a Hermitian operator. So the point is that all quantum states are equilibria of some unitary process, and all quantum states are equilibria of projection. So you can really think of quantum states are equilibria. And this actually is true also for mixed state, because a mixed state at the end of the day is a Hermitian operator itself, and it can generate a transformation, and so it's essentially an eigenstate of a measurement, and is an eigenstate of a time evolution. So what we can think then as pure states, instead of thinking them as something that are completely different from the mixed state, we can keep thinking as pure state as an ensembles, and they're just the ensemble of the lowest entropy. So whenever we have a preparation device, the preparation device is going to prepare something. It might not always be the same. It's going to be an ensemble of an ensemble that we're going to have prepared by the device in multiple settings. And we can think of all quantum states, pure and mixed, as equilibrium of ensembles for some time evolution and for some measurement process. And this is, again, this is not really an interpretation in the sense that it's there in the math. It's not something that I'm saying that I can think differently. No, it's there in the math. So we mean the ensemble in this case in its equilibrium in this sense. And now the idea is that can we argue the converse? Can we argue that the ensemble should be the primary element in physics? Because if we can argue that, we close the circle and we're good. And the idea here is that the goal of physics is to establish laws that are valid in all circumstances. Then whenever we prepare something, you find something else. So all the laws that we write, they're never about something prepared at a particular moment in time. They're something that are about all the possible preparation of a similar preparation with all the possible similar measures. And this is already embedded in physics because in science in general, you have the notion that the experiments and whatever we find has to be repeatable by other agents. So If something is repeatable, it means that you can always do it one more time. And as long as you assume that you can do something one more time, it means that you need to have infinitely copying of the system. And therefore, the objects of your physical law is about all these infinite copies, is about the ensemble. And another way to look at that, to see that we need some kind of equilibria, is the idea that to define and manipulate an object, it must stay the same again for long enough. You have to have something, a time scale, even if it's brief, right? If it decays after a femtosecond, but at least for that femtosecond, the system is there and you can interact with it and you can manipulate and do something. And this is something that we have at all different scales of the physics. So if we are talking about a water molecule, well, the water molecule has to stay the same. And if it doesn't stay the same because we go through a chemical reaction, then we need to change the elements that we are describing. We need to describe the system in terms of atoms, but the atoms must stay the same during the chemical process. Otherwise, we can't talk about the chemical process. In the same way, if the atom does not stay the same during the chemical process because you have a nuclear reaction, well, you must have something else that stays the same so that you can describe what's going on in terms of lower elements, in terms of nucleons. And again, if the nucleons don't stay the same because you have a particle decay, you need something else that, it means that you can't really talk, if this nucleon can't stay the same, you need to talk about something else, and it would be the fundamental factor. So the point is that every level is described in terms of equilibrium of a lower one, and that's sort of how it goes. But the way it ends is that you're going to have these states that you're going to no longer describe, and those are taken as your fundamental elements, below which a description of the system is not possible. And this is what the quantum elements are. These the quantum states are. This equilibria from which you can use to describe the things on top. So that's more or less. And from all of these things, we believe that it makes sense to assume that states are assembled in equilibrium, which is exactly what we have in quantum mechanics from the mathematics. Another thing that sort of makes you even more convinced that ensemble should really be the primary thing is that in classical mechanics, we saw that there were a connection between geometry, probability, and information theory, and the way that it works is that the classical geometric structure is exactly the structure that allows us to define ensembles and entropy, requiring entropy to be coordinate invariant and the marginals of entropies to be coordinate invariant. That's exactly what gave us phase space. So the notion of entropy is tightly linked to the definition of the classical phase space. So if you wouldn't be able to define the entropy, you wouldn't be able to define the classical phase space anyway. And the same is going to be true in quantum mechanics. In quantum mechanics, we have these projective Hilbert spaces where their states live. We have the quantum probability defined by inner product, and we have the entropy defined by von Neumann entropy. What happens is that if you take a mixture of two states of 50% for each, you have a function for that for the entropy of that state, and that function depends only on the inner product, and it is an invertible function. So defining the inner product in quantum mechanics is equivalent to defining the entropy of the mixtures of two states. Therefore, again, you can't define the state space of quantum mechanics without defining the entropies of ensembles. And as soon as you define the entropy of ensembles, you already gave me all the structure of the geometric structure of quantum mechanics. So this, again, is another argument to say, look, clearly, both classical mechanics and physics are about ensembles. That's what they are describing. And the pure states, the point in the classical phase space, and the pure state in quantum mechanics just represents the perfect example that in the theory you could have to describe everything. And again, another thing that gives us more ammunition to the argument is in I know that this is something else. This one thing that it's sort of confusing when we look at pure state in quantum mechanics is that it makes it, the uncertainty principle makes it look like there are some states that are more determined than others. And so it would kind of feel that these ensembles that the pure states are describing are different. But again, the way that we should really properly describe the let's say the spread of the ensemble is not really the uncertainty, but it's the entropy. And what happens when you increase this product, it's actually you're putting a correlation between the x and the p, and this does not take into account that it doesn't have a correlation. Another thing that again can make us understand that all pure states of quantum mechanics are essentially giving us the same type of uncertainty is that you can always create a unitary transformation that moves one state into the other. And then you can use that unitary transformation to construct some observable that saturates the uncertainty principle, that it's there as an equal. And the way that you can do it is we basically say you take a Gaussian state. The Gaussian wave packets will be the one that has an equal in the uncertainty principle for position and momentum. And then you take a unitary operation between the Gaussian state and your target state, and you're guaranteed that this always exists because in the Hilbert space, that's just a rotation. So you're just mathematically just rotating from one to the other. And then you can consider A as U dagger XU and B as U dagger PU, which is basically the observable transformed according to the unitary operation. And you calculate the expectation value. And what you find is that the expectation value, when you expand, is equivalent as taking the expectation value of the Gaussian state with respect to x. And the same thing is for a square. It's just the expectation value of x squared with respect to 5. And the same thing for b is going to correspond to p, and b squared is going to correspond to b squared. So when you now do your calculation of your uncertainties, you're going to find that the product of the uncertainty of A and B on the target state is the same as the product of the uncertainty of x and p in the Gaussian state, which is h bar. So the point is that all of these ensembles, these pure states, always have some observables that are kind of like maximized in terms of uncertainty, and therefore the information that you have encoded in each of these pure states is exactly the same. And so you can really think as all the pure states as ensemble at the same level of entropy, and you can always move from one to the other in a way that sort of preserves that entropy. And this is saying the same thing. And so if we step back, what we're basically saying is the quantum states are at least ensembles in equilibrium. Of course, one can add more things in their interpretation of what the ensemble actually is, an ensemble of what, and so on. One can do that, but for us, we want to be minimal. We just want to say the minimal thing that we need to say, and the minimal things we need to say are just ensembles in equilibrium, meaning that there are equilibria of a projection, of a measurement. If you make the measurement twice, you get the same thing. And they're equilibria of a time evolution, meaning that there is a time evolution for which those things are actually equilibria. They stay the same as a dynamical equilibrium. And this is pieces from other things. Yes, one of the things that we need to do is that there is other literature that is sort of talking about some of these ideas. There is something called the eigenstate thermalization hypothesis that really shows how pure states can actually be seen as equilibration of a lower level within quantum mechanics, so that you can actually say that the wave function of an atom is actually an equilibration of the lower elements, and so that would be nice to sort of connect and see that the whole what we're saying is consistent with all these things. So that's one thing. So we talked about states, and now we should actually talk a little bit about processes. And in quantum mechanics, again, you have this problem that you have two types of processes. One is the measurement, and one is the time evolution. And the idea what we want to show is that the time evolution is for deterministic and reversible processes, and that the measurement is the projections in general are processes that have equilibrium, so that you start with something and all the outputs are equilibrium. If you have that, then you have a measurement. And so you have these two different types of evolution because you are requiring two different types of evolution. And clearly, the projection is not gonna be something that it's an isolated deterministic because the final element is not determined by the initial element. So clearly the domain of applicability of the two processes are distinct. And both are, at the end of the day, idealization, because, again, the deterministic and reversibility, as we saw in classical mechanics, is equivalent to saying isolation. And as we said before, nothing is perfectly isolated. So, again, this is an idealization. And again, even this is an idealization that the equilibria, most of the time, you would have to wait for infinite time, which you don't have anyway. And so again, this is also an idealization. So the problem that we have two different idealization doesn't seem such a problem to me. But there is still a way to reconstruct, to combine the two, to show that one can be derived from the other. Typically, people want to derive the deterministic and reversible processes from a measurement, and that really cannot be done unless you construct a lot of things that are outside the theory. But what you can show is instead that you can recover deterministic and reversible evolution from a series of measurements. So you can think of the deterministic and reversible evolution as something that keeps measurement something slightly different at each moment in time and constructing the evolution. So let's look a little bit more on how things work. The best way to understand all of this is by looking at the space of mixed states instead of pure states, because projection are things that increase entropy, and it's much better to see if we look at the space of mixed states. Unfortunately, the two-state system is fairly simple to describe. All the states of a two-state system can be understood as point on a surface of a sphere, which is called the Bloch sphere. And all the mixtures can be understood as point is at the very interior of the sphere. So, for example, if I have an equal mixture of 50% and 50% Z up and Z down, I would get the middle point. And the middle point can also be obtained by doing a 50% mixture of the spin left and right. And this is exactly the thing that is different in quantum mechanics is that ensembles do not have a single decomposition in terms of pure states. They can be decomposed in many different ways. And again, you can imagine that all the pure states on the Bloch sphere have entropy zero, as we said. As you increase, as you go towards the center, the entropy increases, and you have your maximum entropy here at the needle point, which is the entropy 1. So if you understand that geometry, now we can understand what unitary times evolution and measurement do. When we're doing a time evolution, we are making a change at constant entropy. So the only thing that we can do is move around on the sphere. And because the mixtures also have to keep the entropy the same, what happens is that the only possible motion is essentially circles around the sphere. So if I'm here, I'm going to go around the equator. If I'm here, I'm going to go to a circle and so on. And Again, you can see if this is the lowest energy state and this is the highest energy state, you're circling around at sections of the ball in which the energy is constant as well. And so the angle, how fast you go around, is going to be determined by the difference in energy. And of course, you can see that the two eigenstates are anequilibria because the circle at the poles will become a point. And so if you are on the North Pole or the South Pole, you are rotating, you're staying where you are. So you can see sort of geometrically that these elements are an eigenstate of a time evolution. Of course, you could put, if you could pick any other two antipodes and then rotate around that axis. So this is how it works for time evolution. Of course, if the system is multidimensional, these rotations are going to be very, very hard to visualize, but the composite is the same. You have some rotation somewhere. Now, what happens in the measurement, I like to divide it into two steps to make to really understand what's going on. It makes it easier. So the first one is, let's say, a preparation more than a measurement, because you're preparing a mixture of possible outcomes. Because the idea, if I am measuring, let's say, the energy here, the output is only the only two eigenstates are going to be the two poles. So at the end of the day, I'm going to have to be either in the North Pole at one energy or the South Pole at the other energy. And so if you imagine that you are you have an ensemble that is given by any of the mixture inside the ball, the first thing that you're going to ask is, what is the ensemble that I would predict if I first started here? Well, if I started here, what I would predict is that I'm going to have equal mixture of E1 and E0. The idea is that this energy, right, is only defined essentially in this set of ensemble. Is not defined in any of the other ensemble. And so the first step is to project on this line. And once you have an element on this line, now you have the same thing that you would have in a classical measurement. You have a distribution on something and you don't know which one it is. And this is where you collapse to a single state, either E1 or E0, because you have figured out what the actual state is. And so this is the thing that sort of looks a little bit more like thermodynamics, because the first projection, the real projection, the one that projects you to the states, to the possible mixtures, that's something that increases the entropy, and then the determination of the outcome is the thing that decreases the entropy because you're adding information from outside the system. And so we can look at this projection idea and how it's linked to thermodynamics a little bit better. We saw before that we have projections are things that we start with something and then we have equilibria, and then the same equilibria retains, like the same remains. So essentially projections or measurements are linear operations on the state of mixtures that are idempotent, meaning that if applied twice, you get the same thing. And these projections, then you can really think it as a black box equilibration process, something comes in and the outputs are always equilibration. So projections, yes, are measurements, but really you can think it more of that. I get something as an in-state and I spit out equilibrium. And this is something that is very akin to what happens in thermodynamics. You have an equilibrium of an open system. Well, this does not define a number of particles. It will give you a probability distribution on the number of particles because the system at the boundary is fluctuating. The number of particles is changing at the boundary. And then, of course, if I wanted to measure the number of particles, well, I have to stop the system from fluctuating. And the thing how I do it, I just close the lid and I change the type of ensembles. And now I'm in a canonical ensemble instead of a grand canonical ensemble. And now I will have a particular value of particles. I know what the number of particles it is, and then I can go and measure. And so the idea is you start with a grand canonical ensemble. Particle number is not defined. What is defined is the chemical potential. And then you close the lid, you get to a canonical ensemble. The fluctuation that I had before become a probability distribution on the possible ensemble, which are now defined by the number of particles. And note that the chemical potential is not defined on this ensemble. It's the number of particles that are defining the ensemble. So you see, even in thermodynamic and statistical mechanics, not all variables are always defined in an ensemble. And if you want to have a variable defined, you have to go and change ensembles. And whenever you change ensemble, you're gonna create some uncertainty unless you are in a thermodynamic limit. And if you are in a thermodynamic limit, this probability is very peaked. And therefore you say, okay, well, it's very peaked. I'm going to be 100% in that final state. So I don't have this problem of a final distribution. But technically, you do have it. You don't know exactly what number of particles you have. And so we can think of quantum states as a different ensemble identified by different quantity, and we can think as the projection as a measurement as some type of equilibration process in which we change the boundary of the system, and now the system has to adapt to the boundary and pick a final ensemble in the same way that you would have in thermodynamics. I don't think I need to go through this. This is a little bit more of details of how the evolution looks in terms of the Hilbert space instead of the projective space where states live. You basically have the rotation in the different subspaces. And but this is more important, is we can recover unitary evolution from the notion of deterministic and reversible evolution. So if we say that we have deterministic and reversible evolution, then it means that the difference between the final state and the initial state is just a function of the initial state. It's an operator that is applied to the initial state. And since we want to map things one-to-one, the final state has to be there with 100% probability. We have to go at one and only one final state. And if you do the calculation from these two requirements, what you find is that this time evolution operator has to be anti-Hermitian. And if it is anti-Hermitian, then it can be written as some type of Hermitian operator multiplied or divided by I. So now this is self-adjoint. And we put by convention our H bar so that the T and H have the correct unit, and therefore you basically went from assuming deterministic and reversible evolution and going to unitary evolution. And of course, the reverse is true. A unitary evolution gives you deterministic and reversible evolution. If I give you an input state, you have the final input state, and the final input state is going to be normalized, and it's going to have 100% probability. So that's one way to derive unitary evolution. And then the other way that I was talking about, you can also rederive it as a quasi-static evolution. So the idea, if you imagine that you start with spin up and you change the polarization right away, then you force the system to choose between one direction or the other with 50% of the time. But the idea is that if you take this polarimeter and you put lots of them, all like slightly rotated with each other, then what you're going to do is you're going to make that change small and small and small, and then you're going to have a high probability to end up in the direction that you rotated. Ideally, if you make infinitely many steps, you are going to be rotated with 100% probability. And mathematically, you're basically requiring that the projection between the present state and the future state is 1, as you go from probability 1 from one to the other. And again, if you do the calculation, you find again that the time evolution operator has to be anti-Hermitian, and you get the same result. You get the same unitary evolution. So you can think about unitary evolution as these two things, either just deterministic and reversible process, it's isolated, Or you can imagine that the boundary between a system and environment is changing according to the state of the system. So the state of the system is telling you how the environment, the boundary between the environment and system is changing, and therefore it's telling you which is the next equilibria and which are the values for the next equilibria. This is where sort of the thermodynamic part it becomes different in quantum mechanics, because you have a continuum of possible equilibria that you can go instead in statistical mechanics and in thermodynamics. You open a jar or you close a jar. It's very binary. Okay, so again, we have this two idea. We have deterministic and reversible evolution that gives us a unitary evolution. We have this black box processes with equilibria. We don't know what happens inside. You just know state comes in and equilibrium comes out. This gives a projection. And then we have a way to recover deterministic and reversible evolution of quasi-static evolution. And note that this quasi-static notion of quasi-static evolution, if you look at how do you do calculation in quantum field theory to do scattering amplitudes, to recover scattering amplitudes, what you basically do to model a process that happens in a particle accelerator where two particles comes in and other particle comes out, what you do is that you put in an in state at minus infinity and you put the out state at plus infinity, and you calculate the scattering amplitude on this infinite time. And this already feels to me that you are sort of making a quasi-static process. So you're taking the thing that happens in I don't know, femtoseconds or even less, and you're stretching it out to make it a little bit more adiabatic and described. So the point here is that every preparation is a measurement, and time evolution prepares the system at each time, and therefore you can see time evolution as a series of measurement, and that's why you can argue that this quasi-static evolution recovers the deterministic and reversible evolution. And so you sort of solve the measurement problem in this way. It's like the inverse way of doing it. We're recovering this from this and not the other way around. Okay. So in a nutshell, projection are processes with equilibria, and measurements are processes of equilibria. Unitary evolution is deterministic and reversible evolution, and we can resolve the measurement problem using this trick. And what we still need to do is take all of this and write it as a coherent thing, but we're basically getting ready to do that. I don't know how much time we have and how many slides do I have to go through. One of the characteristics that we want to argue even conceptually is that quantum mechanics can be seen as irreducibility. So this notion of equilibria already tells us that we can't really tell what the parts of the system are doing, because if we were able to do it, then we would have to have a lower description in terms of something smaller and describe that. And we talked a little bit about yesterday, even asking that you do not have access to the internal dynamic is enough to get a qualitative sense of the quantum effects. If we are able to stretch everything in a single point of position of momentum, then of course we would know what the whole system would be doing, because all the system is there and it's moving, it's doing the same thing. And so if we say, no, we can't access the internal dynamics, you're already saying, well, we must have something that is spread in position of momentum, otherwise we will be able to know everything. And once you say I have something that is spread in position and momentum, you get already no locality, because you can't interact with the system in only one part. Because if I were able to interact with the system only in this region, then I would have access to the internal dynamics of what happened in this region. And therefore, the system, if I assume that I have no access to the internal dynamics, the system has to be no local. But this also means that superluminary effects cannot carry information if they are inside, because, again, I would be able to know what the internal dynamic is. So even if there are superluminary effects within these ensembles, you can't really tell what's going on in between. And And again, the probability of transition can be understood essentially as different equilibria sort of switching possible evolution among each other if we look at entropy in the way that we define it in the other talk. And just by that, you would get that the probability of transition has to be symmetric, because if I say that this number of possible evolution go here, then it means that the remainder, this part also has to go to the other side, because the total here and the total here and the total here and the total here has to be the same. So this decomposition has to be equal in all sense. Let's skip this. Another way to consider reducibility is really in terms of ensembles. This, if you look at the space of ensembles, you really see why classical physics and quantum physics are different. In classical mechanics, whenever you have two ensembles, you can detect that there is an overlap in two ways. Either you can find a smaller distribution inside that can be seen as a part of both, or you can just look at the inner product and see that they're not orthogonal. And in classical mechanics, these two ways of distinguishing overlap is the same. But in quantum mechanics, there actually is not the same, because you can have pure states that are not orthogonal. But of course, they're not going to have a common components, because there is nothing that resolves better the overlap of the two states. And this is kind of what the irreducibility looks like in terms of the ensemble. If you have an overlap, you can't always resolve the overlap and tell what's happening in the overlap. You don't always have access of something that it's smaller and smaller and more refined in terms of the description. Another thing that comes out for free from thinking like this is that you have two ways of thinking of probability distributions. One is in terms of a statistical distribution of matter that is actually spread across space. Another one that is a probability distribution where the matter is concentrated in a point and it's just jumping around. And the point is that you can distinguish these two things only if you have access to ensembles that are more refined. If you don't have access to ensembles that are more refined, which is the case of reducibility in quantum mechanics, then you can't distinguish between these two things. And this thing corresponds to the wave nature of the quantum system, something that you can think it as being actually spread out and moving as one thing. And this corresponds to the particle nature of a quantum thing. You have something that is jumping around in terms of a probability. And the point is that if you're saying that your system is irreducible, you already admitted, well, I'm not going to be able to distinguish between those two things. And so the type of ensembles that I'm going to have, they're going to be something that it's in between, that I can't really say that it's one or that it's say that the other. If I were able, then I would have a lower level description, and then I would have the problem on the lower level description, that you're just kicking the can somewhere else. Another thing that is interesting is if you look at the space of ensembles, you can always imagine in quantum mechanics that all pure states have zero entropy, and then you go inside and you increase the entropy. And if you have an infinite dimensional space, you can also get to infinite. Well, you can't get to infinity, but you can arbitrarily large ensemble and arbitrarily large entropy. And what is interesting to see is that in the classical discrete, you have the same, the pure state are at zero, but the surface is not continuous. So you can't have a deterministic and reversible evolution on a discrete space, a classical space, because you can't transition, with time evolution. You don't have a continuity. In the classical continuum, you do have the ensemble, the zero entropy form a continuum, but as I said before, you can even have these ensembles that are more refined, so you can have arbitrarily low entropy. And so kind of the quantum space kind of looks like the classical continuum, where you have chopped off the states from 0 and below. Of course, it's not exactly the same because, but you would have, for example, the non-single decomposition of states of entropy higher than 0 in terms of the states that are equal to 0 in the same way that you would have in quantum mechanics. So you do recover some of this property. And again, these are things that I'd like to explore more given the time. So takeaway is that irreducibility is really the key difference of quantum system, and that all quantum properties can be qualitatively understood in terms of that. And then we have sort of physicsy, hodgepodge argument to say these things. We really like to do this mathematically, but we need the proper mathematical machinery to do it. I think I'm going to skip this in the interest of time. Another way to sort of look at the problem of quantum mechanics not following a classical probability. Typically, people have looked at things like Wigner function, where you have negative probability. We're looking at instead a type of probability that it's not additive and then becomes additive in essentially on a context, on the eigenstates of observables. And we are working on that. We'll be talking about it tomorrow when we talk about ensemble spaces. And I think I'm just going to skip all of this. And we're going to be talking a little bit about more of the classical limit. What we want to show is that typically the picture that one is given, that is typically this one, it's not really correct. So typically you basically say, I have slow system and fast system, where slow means very small compared with the speed of light. And this is the difference between non-relativistic and relativistic physics. And then you have something for a small system or big systems, and small system are quantum mechanics and big system are classical mechanics. And then when you add fast, you get relativity quantum field theory. And the other option is to make the limit of h bar going to 0. And the point is that this doesn't quite really work. We have big systems that still exhibit quantum effect. You can keep coherence along kilometers. So saying that kilometers is small doesn't really work. And the other problem is that saying that h bar goes to 0, h bar is a constant of nature. It doesn't go to anything, it stays what it is. So there has to be something else that is small or big with respect to the other constant. And what we think is that these two should be replaced by instead low entropy and high entropy, because as we saw before, low entropy is really exactly where things break down. So what we hope to show is that if you do quantum statistical mechanics at on a high entropy state, you can basically use the classical statistical mechanics, and the mistake that you make is small. So one way to look at this is if you do a two-slit experiment. This is again a qubit. It's the state space given by two states, which is S1 going from the first slit, and S2 should be S1 going through the second slit. And you would get this is the first state, and this is the second state, and the maximum mixed state is essentially this, the sum of the two. Now, of course, if you open up both slits, you get an interfering pattern, and the interference pattern depends on the phase difference of the wave function that goes through both slits. And so you would have a 0 phase shift or a 180-degree phase shift, and here they're giving you in two columns. The point is that if you do an equal mixture of the two, you still get the same pattern that you would get here, because it's the same mixing mixed state. And so the point here is that uncertainty on quantum variable, even on things that in principle are quantum effects, can still be represented as uncertainty on the classical variables. So if you see that, if you imagine the space of mixed state here, the more you increase the entropy, the more you are going to be closer to the axis, and the axes are going to be representing a classical probability distribution in terms of the two elements that you would think that are more classical. So the idea would be that would happen if you have, especially if you have an infinite dimensional case, you get closer and closer to these classical elements, and you can sort of get away with using classical mechanics. And the point of doing this is that there is no actual mechanism to recover classical mechanics. It's just like in relativity. If you are at low speeds, you can get away with Galilean relativity. If you are at high entropy, you can just get away with using classical distributions. And one of the things that we would like to do is essentially recycle all the proofs where you say that h bar goes to 0. And the idea is that really what happened, what you care about is the difference in entropy between the pure state and the state that you're doing. So if you're increasing the entropy of the state, you're increasing this difference. But one way that you do it, instead of looking at it like this, you could keep the entropy the same and make the entropy of the pure state goes to 0. And you will get that in the limit, the entropy is the same. You're making an entropy difference. And so the idea is that doing this entropy h bar goes to 0 would be interpreted physically as I'm always rescaling my entropy to be smaller and smaller, and that's what I do it. But the more physical way to do it would be less. So if we're able to make this transformation, we'll be able to get those proofs and use it for us and give physical meaning to all the proofs that says that h bar goes to 0. And so basically, again, classical mechanics, we hope that can be recovered with the high energy, high entropy states, and there is no mechanism, and the high entropy essentially hides the quantum effects. And of course, this is a conjecture, and it needs to be proven, and we still need to do that. But chances are it's going to work out as these things are cases. So wrapping up, quantum mechanics can be seen as a combination of classical mechanics and thermodynamics. We are trying to work towards a minimum interpretation that uses the concepts and only the concepts that are strictly in the math. So ensembles and equilibrium is supported by the math, and so we're going with that. And the ongoing goal is to clean up all these ideas and making a consistent conceptual and mathematical theory that is supported by experiments. And that's it. And we can open up to questions.
Yep, Tobias put a few questions in the chat.
Okay. Let's go for that. Okay, so when you say we cannot study the parts, then we also cannot be sure that parts even exist. Correct. At least it's not part of the empirical realm. Correct. But it's important for you to define what a part is, or you get away with that. You get away without it. Because what you're basically going to say is just, look, the thing that we can prepare are ensembles. And ensembles can mix, and I have the smallest ensemble that I can have is this. And I don't know ensembles of what, but I know that these are the things that I can go and prepare. The fact that there is something smaller, it's like somebody has to go and say, oh, I prepare an ensemble that is smaller. If I can't prepare it, I can't prepare it. And in that sense, I'm not talking about a part. And the ensemble, the pure states become just the best ensembles that I can prepare. And then you can stay there and say, oh, what ensembles of what? There must be hidden variables. And you can do that, but all the power to you if you find a hidden variable theory. But we say, well, those are outside what we can prepare and measure experimentally anyway, because they're not ensembles. And then quick idea, since you split the measurement process in two, you could execute only one part of it? Yes, you can. And like use a measurement event, but ignore zero. Yes. And that's exactly what you would do. Yes. So it's like, it's the same thing in classical mechanics. You flip a coin and you don't see the result. You just have a statistical distribution. The thing is that what this tells you is that the measurement does that change. It takes something and it puts it in this high entropy state. That's something that is actually happened. And things like the quantum Zeno effect are things that are telling you that something is happening. There is an actual change. You can't just say, oh, I just updated my wave function because I actually interacted with the system.
So this is a non-unitary process, right?
No. Yeah, yes, it's not a unitary process, yes. But it's still a projection.
Yeah, okay.
And like the the way I said yes to uniform process, because I was thinking a more general constraints that that processes must have is that a process must take the process applied to the ensemble must be the ensemble applied to the parts of the ensemble. Right? You still need some linearity. And that's something that both unitary processes and the projection have. And it's something that you must require whenever you have a process that it's applied to ensemble. That the process, the evolution of the mixture is the mixture of the evolution.
Okay, but if I really do a measurement, I select the one outcome, right? This is no longer linear. I just update my knowledge.
That's updating your knowledge. You're taking something that is the result of the experiment, and you're effectively, you can think it like this. You're actually preparing a new ensemble that then you're going to use for the future. Right? Because now you have new knowledge, you define something more, and I can say, oh, now I can be sure that this is, and every time that I'm going to repeat this, I'm going to measure this, and I'm going to be in this ensemble. So effectively, you have taken one ensemble and you split it into two, and now you can talk about this independently for this and proceed with your time evolution. And that thing, the update, is something that is external. Like it's not there in you're taking an interaction with something else and updating. And that's more akin to what the Bayesian you talk about. But it's the same thing in classical mechanics. I give you a deck of cards. You don't know what the deck of cards is. You look at the elements, and now you know what the deck of cards is. Okay. And a small paradox I cannot resolve. Are there any restriction how fast, often I can measure the position? I could measure position alone with arbitrary position and get an almost classical trajectory. Yes, that's more or less what happens in a bubble chamber, a wire chamber in a particle detector. You really see a trajectory, and you calculate what is it called? The charge. You calculate by looking at the curvature of that classical trajectory because you have a magnetic field.
Yes, but wouldn't you not you be able to calculate the velocity and then the momentum? And then I don't know where the uncertainty principle would like kick in.
You measure the momentum from the gradients of curvature, and the charge, is of course a binary thing. So, then you just by whether it curves one way or the other way in a magnetic field. And I don't.
In a curvature, I know that. But I mean, if I know the position at every time, position alone I can measure with arbitrary precision. If I know the time with arbitrary precision, I can calculate the velocity with arbitrary precision, I guess. And then I would know the momentum with arbitrary precision. I don't know where the uncertainty principle would break this argument.
I do those kind of experiments, and in practice, we're not anywhere close to a quantum limit, but I don't know if I have an answer for the conceptual question.
So probably there are going to be limitations on the measurement device itself that are going to kick in. You're not going to be able to cheat it. So it's probably going to depend also on the measurement setup. So of course, with wire chambers, you're not going to be able to have infinite precision because at some point your wires are going to be too close to each other, and
Yeah, well, it's you get smaller with things like silicon and semiconductor, but yeah, it's still like micron scale, not anything that tiny. It would be interesting to try to think a little bit more conceptually about what the limit is, if there is one, just conceptually.
Is it okay if I contribute a little bit on this?
Oh yeah, go ahead.
So I asked the same question to one of my professor, and to one of the example that he gave to me is that if you want to really understand, let's say the position of a particle, then you may want to hit it with like some very fast photon or something like that. And when you make collision, that's how measurement is made usually. Usually, I think when you have collision with an object, you inevitably changes its velocity and its position. So the more precise you want the position of an object according to him, you want to hit it with like more energized photon, and that usually results in faster velocity. So I guess that's where the uncertainty kicks in experimentally, at least the one that I can imagine.
Even theoretically, if you make the precision in space very small, of course the uncertainty momentum goes up, and then it's also more likely that it has high momentum and high velocity. That totally makes sense. But I'm still not sure why I wouldn't be able to determine this high velocity with high precision. That's the problem that I have.
I'm not sure if we can go arbitrarily small in like how fast we measure the position of something.
Yeah, that's the point. Is in classical, like in the typical description of quantum mechanics, some law that tells me how fast I can measure things. There is, of course, an uncertainty principle also for time, but I looked it up and it seems to depend on the commutator between the Hamiltonian and the observable I want to measure. But let's say I want to measure position, then if it's a free particle, then they commute. No, they don't commute, because then I have P and X. Maybe that's it. Okay, I need to look into this.
Yes,
Maybe that's it.
but yeah, so as I said, on the measurement device, I'm pretty sure there is going to be some kind of.
But this is
And then
experimental physics.
regarding what Shengli was saying about using a very high energy photon, say, to have a very short wavelength to resolve, just imagining the position of, say, an initially stationary particle, trying to get very good position information on where it is. This will relate to some of tomorrow's material on references and physical mathematics, like what it takes to do to do science, that you always need some kind of reference, and you're not going to be able to get to arbitrarily small determinations of distance scales or time scales, just from conceptual arguments that will be presented tomorrow. Can move it. Yep, next question.
Hi, I might have missed this in the beginning, but how do you define ensembles? It is the same how we define it in StatMech. Is it a consensus that ensembles are minimal sets for the basis of quantum mechanics? If not, how does the math suggest that it is the case? Okay, so we are thinking of ensembles, and we're going to talk about it, like the more mathematical definition, we're going to approach it tomorrow. But the idea is that, as I was saying before, we have preparation devices that prepare some states. And we want to make statements on the fact that whenever I prepare something with these preparation devices, I can do a bunch of things. And so the ensemble, it's seen as the sort of collection of all the possible single preparation of all the measurement devices that are similar to the one that you start. And so it's not defined in the sense that I have a statistical distribution on something. I just have measurement, the preparation device and preparation device do something. And the idea is that the pure states in quantum mechanics are, for a given system, the best preparation devices that you can make. That is, they are the one that cannot be seen anymore as a mixture of two different preparation devices. So a mixed state in quantum mechanics, for example, the maximum mixed state, you can think it as I have a preparation device that prepares spin up. I have a preparation device that prepares spin down in the best possible way. And then I make an equal mixture of that, and I get the maximally mixed state. And so the idea is that a pure state represents a preparation device that cannot be seen as something that is mixture of something else. Technically, the realization is that even when we prepare spin up, that preparation of spin up is never perfect. It's going to be spin up, plus or minus something, right? So these pure states are really our idealization of a best possible device that we can never define in practice, even in quantum mechanics. And so that's kind of why we believe that it's better to talk about ensembles in general, because those are the things that we prepare, right? Even when I say prepare spin up, and you look at the paper, there's going to be a spin up plus or minus the purity of the states and all of that. That's the thing that we prepare in the lab. And it's convenient in the theory that we think about these abstract things that are perfectly prepared, because then the math is easier, because we don't have to, again, if you just look at dimension, the space of all possible mixture is the interior, right? And the space of pure state is just the surface. So I only need to tell you what happens on the surface instead of telling you every point. And in higher dimensional spaces, it's even worse than that. Like the interior is very, very complicated. So it's more efficient to do that. But again, the idea is that the real notion, the thing that we prepare in the lab is an ensemble. And I do think that it also makes the better idea then you think as the ensemble that have a higher entropy as the classical one, because they are vague and who cares, and then you go outside and then you have quantum mechanics, and then who knows, maybe those we are going to see that those ensembles when we go to Planck scale don't exist in a technical sense. There's going to be other things that are a little bit more complicated and so on. So I think this gives us a better picture of how things work. So they are going to be recovered to be the same one that you have in statistical mechanics. But instead of saying, I have the pure states, and then I define the ensembles, I basically say, I have the ensembles, and then I look for these pure states as my idealization. And we think that this is a better way to look at it, because we think it maps more to the physics. Like this is what we actually have.
So in terms of whether it's a consensus that ensembles are the minimal set for the basis of quantum mechanics, that's not the way it's typically talked about now, as Gabriel just said. So we're saying that we should, what you'd see in a typical textbook would be just you're working with pure states all the time in the typical textbook. And we think that it's going to be more fruitful to think of an ensemble and the pure states as a sort of limiting case of the ensembles. And we'll have more on that tomorrow.
And everything that we say, it's already there in the math. So
sure.
Again, we want to, if you want to call this an interpretation, it's like the minimal interpretation. We're trying to look for things that are there in the math. So you have to say these things. And therefore, if you have any other interpretation, you want to add, infinite many words or whatever, you're still free to do it. But you have to still to say these things, because the math says these things. So if you want to agree with the math, you have to agree with this.
I think people who actually do measurements, like that are testing quantum mechanics, would also in practice agree that you're considering ensembles, but that's still not how people formulate it in either textbooks or I think in papers, like, research papers either. Although, of course, when you say you prepared spin up, and whether or not you report some uncertainty on that, yes, of course, there's some finite resolution on your device to prepare a spin up system.
And question, what does level mean when you say every level is an equilibrium of the lower one? I mean level of description. So so this is kind of like, whenever you do a formal theory of anything, you have to define what are your primitive objects. And so even in a physical theory, you're going to have a set of primitive objects. So if you're doing, chemistry, your primitive objects are essentially the atoms. And you study how the atoms compose the molecule. If you're doing, civil engineering, you consider the the material as the material, and then you have different coefficients that characterize your material, and that's it. So whatever you're trying to describe, you're going to be at a particular level. The thing that is most interesting to us, and we're going to talk about it later in the philosophy part, is that the level is also important because the definition of the system is defined at that particular level, because you can disregard the thing that happens underneath. And so if you just say, you know, that a molecule is a series of atoms and it's the description of the atom, well, that's not quite true, because the position of the atoms can wiggle around and you still have the same molecule. You know, in biology, if you have a biological system like, I don't know, a cat, or even us, we are open systems, right? The molecules come in, molecules comes out, and after a year we changed, I don't know how, like a high fraction of all our molecules. And so if you just say, oh, we are describing by the position of all these things, well, that's not really true, because things can flow in and out and you still have the same system. And so you essentially have a hierarchy of descriptions, and it's not really clear. And it's useful sometimes to relate those hierarchy, but I think just dumping everything in one single level and say that that level describes everything, I don't think it quite works like that. And it would be nice to have this like really spelled out of why it can't or if it can and so on. But I haven't seen, especially in foundations of physics, everybody talks about the fundamental level and that's it. And again, even in studying things like an atom and so on, it's interesting to me, how do you get the next level? And especially in quantum mechanics, how it is that when I describe an atom, I'm using the same mathematics that I'm using to describe a single particle. Like, that is the thing that is most puzzling for me for quantum mechanics. Like how it is that even a big molecule, like a buckyball, that is like this soccer ball type thing, you make it diffract and you use the same interference pattern of a single quantum state. And it's a complicated things of hundreds and hundreds of things, right? So that's what there must be some assumption that you can make at both levels, that you basically say, well, at this level, in this process, I'm really not really sensitive to the internal structure of the buckyball. Therefore, that all that degrees of freedom goes completely away, and they become a single quantum system coherent and everything. And again, this is because you're really changing the level of description. I don't know that you would be able to see it if you saw, I mean, if you describe the whole thing in terms of quarks and gluons, I think you would go crazy probably. So
is that kind of why you thinking of using entropy as a way to differentiate quantum mechanics and classical mechanics?
I think that the entropy works as the cutoff to say, this is my level of description. My zero entropy is, look, I care up to here. I'm not sensitive to anything anymore. Mm-hmm. And the idea of really, I have decoupled the dynamics and the description of my system from the internal really means that I have this hard cut of barrier of entropy. And I cannot think that this must be an assumption. It can't be something that is strictly true. It's something that, you know, especially for something like a big molecule, it's something that in this particular process, in this particular set of circumstances, with this particular system environment boundary, I can make this assumption. But if I change the boundary, I must change the description of the system. I need to know. And another thing that, you know, like, you know, particles decay. You have a muon and it decays by itself. There must be something inside the muon that clicks and says, aha, and now it's decaying. But the point is that that dynamics is not accessible to you. And by the fact that it's not accessible, it must mean that the probability of decay has to be the same at each moment in time. Because if you would be different, you would be detecting, I know what the dynamics is doing. And in fact, the probability of decay follows an exponential rule, which means that. So there are a lot of like simple things, simple arguments like this that you can make in terms of, I must be able to decouple and so on. And entropy, as we saw yesterday, is really the thing that allows you to tell you, look, if I have a system that is independent from everything, then you must be able to define its entropy, and it must be the one maximized because it's the one that sort of takes out everything. Yeah. And so that's why I think it's really fundamental.
That almost reminds me of there was once where we learned that the coupling of two spin half particles is no different than a spin one particle. So sometimes I couldn't help but thinking, like, if we ever measure a spin one particle, like how can we ever tell it is not the work of the coupling of two spin half particles? And why are we so sure that it is a single entity by itself, not something else? And this, yeah.
This is related to the research that Christine does on the spin of the proton. Like you have all this mass of the spin of the quarks and the sea of quarks and the gluons and so on, and all of this magically mixes to be exactly one half.
At all times, so to speak. Yeah. Gluon spin, quark spin, and gluon and quark orbital angular momentum.
So again, I think that there must be something that when you assume, okay, I am decoupled from the internal dynamics, then the spin can only be these half integer levels. And there, I really think that there must be a simple argument that allows you to see this, a simple argument that gives you the two different statistics based on relativity. We just don't have them. We just have a bunch of math that we use, and so.
How is physics different from biology if we cannot start with a simple idea and get to something, right? So yeah.
Chris, were you going to say something?
I just wanted to clarify the earlier point you're making about there's fluctuation in the number of particles in the container, and then you close the lid, and you made an analogy to the energy of a quantum system. So you were saying that the quantum system is exchanging energy with its surroundings. When you interact with it, you redefine its boundary, and now you're not sure how much energy is within that boundary.
It becomes a little bit tricky. So it's not really energy per se, because it must be, I can say, you can change what the energy is because you can change, let's say, so say that you have a spin one half system, right? You rotate the energy aggregate states are determined by the magnetic field that you put around. So more than say the energy is fluctuating is that you have your magnetic field polarized in a particular way, and then let's say the system is going to orient in up or down, right? And now you're in an eigenstate, and then you flip the magnetic field abruptly, and now that the particle that was up comes in, you flip the magnetic field, it needs to reorient, and now it has to make a decision. So in both cases, like if you look at the Hamiltonian before and Hamiltonian after, it's still eigenstates of energy, but they're eigenstates of different observable because you oriented the magnetic field in a different way.
Okay. How is the analogy to the number of particles? Like how is that connected? I think I misunderstood that.
Say it again.
How are you connecting that to the number of particles when you close the lid and you know?
Okay, so the sort of the direction of spin in one direction would be if you're orienting the magnetic field up, then your ensembles are defined by the up or down, by the vertical direction. And in the grand canonical, the observable that defines the ensemble is the chemical potential. Then you flip, right, or you close the lid, you change equilibrium, and now the equilibrium is canonical, is defined by the number of particles. and now you change the orientation, your equilibrium is defined by the horizontal direction.
Okay, so you're not talking about like the quantum of energy in the second case, directly analogous to a number of particles.
Yeah.
Okay,
So
thank you.
you talk about at any moment in time, you can think as the quantum state as an eigenstate of a series of observables. Those are the observables that define what type of equilibrium you have, in the same way that you do in statistical mechanics and thermodynamics. Like you talk about NPT, mu PT, like you call these types of ensemble by stating which are the quantities that are well defined.
Mhm.
Like you do that in statistical mechanics. It's not something that I made up. People do it. And so we could label all the pure state or all the states, pure and mixed, by saying this is an ensemble where spin up is defined, or this is an ensemble where spin left is defined. And so you basically have the same thing where you're labeling state by the type of observables that are defined.
Okay, thank you. I think I was just taking the analogy a bit too literally.
Yes. Ideally, we would like to have a formal framework in which we can show that these are exactly the same. We're not quite there yet. So we should move on. I need to refill my water 1 second. So we'll do a break of like 30 seconds and I'll be right back.